I'll get an answer key posted on Moodle as well today. But if you've got questions over anything, please, I'm happy to go over things in my office. I'm more than happy to answer questions, always more than happy to answer questions about things. So we still have one more exam. It's that scheduled for the Wednesday in the last week of class. So it should be, oh goodness, we have Thanksgiving and break in there. I think it's 4 weeks from this Wednesday. Remember correctly, because we have the week of Thanksgiving off as well. So I don't remember right. Anyway, we have the one exam left, and then we got the final as well. Our final is scheduled for 11 o'clock on Monday of finals week, I believe is the time. If I remember right. I can double check that, but I'm pretty sure it's the 16th. Right, I believe that's the right day. So anyway, we'll talk more about final when we get closer to it. So. Any questions over anything at all before we jump into some new stuff today? All right, so some of the stuff that we're going to talk about in this particular section, we've kind of already done up until a certain point when we've done some solving triangle ideas, right? When we've had to figure out what an angle is and maybe do the inverse sine or inverse cosine of something, or set up an application problem where we've had, pardon me, where we've had to set up a triangle and again do an inverse sine or an inverse tangent or something along those lines to find some angles. So we've already done a little bit of this stuff before. What we're going to do though in this particular section and in the next section is not only we're going to look for those ones that are maybe a piece of a triangle, maybe they're an acute angle, or maybe there's one obtuse angle you have to find. But what we're going to be interested in is looking at an equation with some trig functions and finding all of the solutions, not just ones that fit into a triangle. Okay, so that's what the goal is for this one. So in this particular section, we're going to solve what are referred to as basic trigonometric equations. And these basic trigonometric equations look like what we've already already solved before. So they can be written in the form of some function of theta equals a constant. So this t of theta represents a trig function, a single trig function. So what I mean by that is maybe it's a sine theta, maybe it's a cosine theta, etc. And then c is just a constant. Okay. So this is what we mean by a basic trig equation. And like I said, this looks like stuff that we've solved before, right? When you try to figure out the sine of an angle equaling, say, 0.7, maybe that was in some sort of a triangle that you had to try to solve, that was an example of a basic trigonometric equation. So we're going to look at, again, equations like that, but not just the solutions that may be an acute angle, for example, if you're trying to solve a triangle. Okay. So some examples of some basic trig equations. Maybe you've got something like sine of theta equals root 3 over 2. That would be an example of a basic trig equation. Maybe you've got something like cosine x equals negative 0.4. That would be another example. So again, it's not important that I have a theta versus an x. It's just some trig function. All we mean by basic is that I've got single trig function of a variable on the left-hand side, and then equals a number on the right-hand side. These are kind of our basic building blocks of the types of equations that we're going to solve. If it's not a basic equation, we're going to try to break it down into basic equations. That's why we're going to start with basic equations. All right. Notice that these two equations might have different methods of solving them. For example, when I look at this one, do I know an angle or angles that have a sine value equal to root 3 over 2? Can you tell me an angle that has a sine value equal to root 3 over 2? Over 3 does, right? And 2 pi over 3 does as well, doesn't it? Okay. Versus over here, do you know an angle that has a cosine value equal to exactly negative 0.4? No, it's not one that we know, right? We know 0, we know a half, we know root 2 over 2, we know root 3 over 2, we know 1, and then the negatives, but we don't know negative 0.4. So in that case, we would use our calculator to help and get out some approximate solutions. So we'll attack those two things differently, depending on, can we figure out an exact value, an exact angle, or do I need to use the calculator to help me approximate the angle by doing the inverse cosine, for example? Okay. So far, so good? Okay. So there's two main steps in solving trigonometric equations. The first one is that you want to find all of the solutions in one period of the function. Okay? And I'm going to go back to that first example that I wrote down, that sine of theta equals root 3 over 2. So if I'm going to find all solutions in one period of the function, then I better remember what the period of the function is for each of them. So for sine, for cosine, for secant, and for cosecant, what was the period? How long did it take for it to start repeating? 2 pi, right? So the period is 2 pi for all 4 of those functions, correct? For tangent and cotangent, the period is pi. So that's going to be our first goal, is to figure out all of the solutions in one period. So let's go back to the sine of theta equals root 3 over 2. Usually, it doesn't matter what period you use, but usually the problems will ask you to find all of the solutions in the interval from 0 to 2 pi, between 0 and 2 pi, because that's one 2 pi interval, right? One period. If we go from 0 to 2 pi, and again, if you go from 0 to 2 pi, then you go what? You go quadrant 1, quadrant 2, quadrant 3, quadrant 4, and looking for your solutions. Okay? So let's look at the sine of theta equals root 3 over 2. You just told me a minute ago that sine of pi over 3 is root 3 over 2, and sine of 2 pi over 3 is root 3 over 2, right? And we know that those are the only places because there's an angle in quadrant 1 and there's an angle in quadrant 2, right? Okay. So that's be our first step. We'll look for those angles between 0 and 2 pi. So in this case, you would have theta equals pi over 3 and 2 pi over 3. That would be step 1. Figure out, a lot of times, by the way, these will be referred to as the fundamental solutions. So these are the solutions between 0 and 2 pi. And the reason why we like finding the ones that are in between from 0 to 2 pi, doesn't really matter which of the 6 functions you're talking about, even tangent and cotangent. If you find them all in 0 to 2 pi, then you've gone all the way around the circle, right? You've gone all the way around all 4 quadrants. When you start adding 2 pi again, it repeats, right? So that's the second part, is using the repeating part, the periodic nature of our trig functions. We use the period to describe all solutions. Okay, so here's what I mean by that. And I'll write it on 2 separate lines. I know that pi over 3 is one solution. Pi over 3 is over here in quadrant 1, right? If I rotate all the way around another 2 pi, I found another one. If I rotate down another 2 pi, I found another one. Anything that's coterminal with pi over 3, remember coterminal, the terminal side lands in the same place? Anything that's coterminal with pi over 3 is also a solution. So do you remember how we described coterminal angles? Right back at the beginning of the semester, remember how we described coterminal angles? What did you add or subtract to the angle to find a coterminal one? 2 pi or 4 pi or 6 pi, or subtracted 2 pi or 4 pi or 6 pi, right? We did multiples of 2 pi, correct? So the way that we typically write that is we talk about adding a multiple of 2 pi. So it's pretty standard. I'm going to write down what this n means here in a second. This is pretty standard practice for how we write it. Sometimes you might see this with a k rather than an n. Letter doesn't matter. The important part is that we're doing multiples. So this part right here is just representing that I'm taking some integer, no fractions, an integer, multiple of 2 pi. So maybe I make it 0 and I'm at pi over 3. Or I put a 1 in for n and I add 2 pi. Or I put a 2 in for n and I add 4 pi. Put a 3 in for n, you add 6 pi, and so on. If I put negatives for n, you're subtracting multiples of 2 pi rather than adding multiples of 2 pi. Okay? So a lot of times we'll just write the little disclaimer on the end that n can be any integer. Again, sometimes you might see it represented with a k rather than an n. The letter doesn't matter. Doesn't matter what letter you use to represent it. The important part is that this letter, whatever it happens to be, represents an integer. Okay? Not a fraction, not a square root, not a log, right? An integer, something that's a whole piece, right? No decimals. Does that make sense? Then you would do the exact same thing for the other one. If you remember back to when we were doing graphing with our trig functions, we wrote this same notation when we looked at x-intercepts, right? Where did it cross the x-axis? We did the same notation when we did asymptotes for tangent, right? Same kind of idea. So this is just this is stuff that we've already done. We're just going to apply it to solving equations. So far, so good? All right. So this is doing the example where we have an exact value. I believe the next one is also doing an example of when we have an exact value. So let's look at the next one where it says sine of theta equals a half. Step 1 again, find all solutions in one period. And ordinarily I would just say, find all solutions in 0 to 2 pi. Don't try to be fancy about it. Look in the interval from 0 to 2 pi and go from there. Now, first thing I notice is that it says the sign has to be positive, right? It says it's equal to a positive 1/2. If it's equal to a positive 1/2, what quadrant are you looking in?
First and second.
First and second, right? So I'm looking for an angle in quadrant 1, and I'm looking for an angle in quadrant 2 that has a sine value of a half. Well, if the sine's going to equal a half, what's one of your angles? Pi over 6. That's the one that's in quadrant 1, right? The other one, in quadrant 2, what pi over 6 angle lives over in quadrant 2? 5 pi over 6. Good. So again, this is what other books and what I typically refer to as are the fundamental solutions. These are the ones that are the solutions to the equation in the interval from 0 to 2 pi. So that's step 1, find those. Step 2 is find all of the solutions. And again, the way we find all of the solutions is add multiples of the period. Again, you might see some people use a K rather than an N. I typically use an N because it's integer, so it sounds like N, right? Okay. But some books will use a K. Also, you may see it written with the N in front of the pi this way. It doesn't matter which way you write it. It's multiplication, so it doesn't matter the order. So either way works. I don't care which way you do. And I'm not going to make you write out where n is any integer every single time. If you write an n, I'm going to assume you mean an integer. Okay. That's pretty standard in math. The letter n is typically reserved for integers, not fractions or anything else. Okay. So you can just write it as 2 pi n, and I'm happy. Okay, this okay? So let's look at the next example. That's secant a negative root 2. We'll worry about the last part when we're done with finding all the solutions. Let's first find all of the solutions. We want secant is equal to negative root 2. Well, sometimes it's a little harder to think, at least in my mind, it's a little harder to figure out where the sequence is equal to something. My brain likes to do sines and cosines and sometimes tangents. Okay. So one of the things that you might do when you're trying to find these fundamental solutions is rewrite the equation so that you're in terms of sines and cosines, or maybe you have to do a tangent. That's okay. If I wanted to rewrite this involving, well, which function would I rewrite it involving? Cosine. If I wanted to rewrite this as cosine if theta equals something, what would it equal? Negative 1 over root 2. Good. We would just take the reciprocal of both sides, right? And now, 2 steps. Find your fundamental solutions, then find all the solutions. Okay? Find the solutions in 0 to 2 pi, and then just add multiples of 2 pi. Okay? All right, so first off, I notice cosine is negative. Where is cosine negative? Second and third quadrants, right? So I know that my typically these have 2 solutions, right? Usually, they don't all have to have 2 solutions, but usually they have 2. It's negative 1 over root 2, so there's going to be a solution in quadrant 2. There's going to be a solution in quadrant 3. If I just look at the 1 over root 2 part, or root 2 over 2 part, what reference angle are we talking about? For a reference angle, cosine of what equals root 2 over 2? Pi over 4, right? So what we're looking for are the pi over 4 angles that are in quadrant 2 and quadrant 3. What are those?
3 pi over 4, 5.
Good, yep. 3 pi over 4 is the one that's in quadrant 2. 5 pi over 4 is the one that's in quadrant 3. Those are the fundamental solutions. Typically at this point there's 2, okay? We're going to be doing, later in the next section, we'll have where it's a trig function of a multiple of the angle, and then we have to do a little bit of extra work, but it's not too bad. Okay? We'll talk about that when we get to it. All right, so far so good? To find all of the solutions, what do we add on the end here?
Plus 2 pi.
Yeah, 2 pi n, good. Add those multiples of 2 pi on the end to get you all of the solutions. This would be it if it didn't ask for that last bit. It says list 6 specific solutions. Okay. Well, Two of them are really easy. I can just cover that up, right? And I've got two solutions that are pi over 4, excuse me, 3 pi over 4 and 5 pi over 4. So, and this is how we're going to find them, by the way. If you just put in 0 for n, you get 3 pi over 4 and 5 pi over 4. But again, remember, we should be able to plug in any integer for n and get more. So what do you get if you plug in 1 for n? Good. All right. So let's figure out where these came from. This one is 3 pi over 4 plus 2 pi times a 1, right? Plugging in 1 for n. And then, of course, this one is the 5 pi over 4 plus 2 pi times 1. Basically, you're just adding 8 to the numerator, right? 2 pi is 8 pi over 4. So just adding 8 to the numerator. So if you wanted to find two more where you let n equal 2, what would you get? Good. And the other one? Good. Yeah, 21 pi over 4. Again, all we're doing is just adding another 2 pi, right? We're just going up another multiple of 2 pi. So again, you can just add 8 to the previous numerator. So then if you wanted to do when n equals 3, you would get what? 27 and 29 pi over 4. If you wanted to add another 8, you get 35 and 37 pi over 4, and so on up the line. You could also do negatives. There's nothing special about going up positive. You could do -1. In that case, you would subtract 8 from the numerator. That's 2 pi is 8 pi over 4, right? So you would get -5 pi over 4 and -3 pi over 4. Subtracting 8 from the numerators rather than adding it. It will give you the same answers. And you can do this all day. I'm not suggesting that you do, I'm just saying you can do this all day. And into the next day, and into the next day. The idea makes sense, what we're doing? If you think about it graphically, you don't have to draw this, I'm just going to draw it real quick. If you think about it graphically a little bit, remember your cosine graph goes like this all the, oh, that's a terrible graph. That's all right. Looks something like that. Vaguely like that. What we're doing is, if you look at where it crosses that -1 over root 2 line, we're just finding out where all these intersection points are. And notice there's a bunch of them, right? That's what we're doing. And it makes sense that we can get more and more and more and more depending on how far the graph goes out. Questions on that one? Everybody seems super happy about it. All right, let's do the next one. We're being asked to solve, you know what, I'm going to skip over the next one for a second. Let's go down to the one with a tangent. Tangent equals root 3. Tangent's a little bit different. I'll jump back up to the previous one here in a second. This one just has the exact solution the previous one did. So I just want to jump it down. Tangent is just slightly different because notice for the sine and the cosine, we needed to go all the way around to 2 pi to find all the solutions because the period for sine and cosine is 2 pi. But what's the period for tangent? pi, right? So I only need to find the solutions to the equation from 0 to pi, and then I can write down all the solutions. So here, again, let's do the solutions in one period from 0 to pi. First off, I'll notice that tangent's equal to a positive number. What quadrant are we looking in? The first and third, but then again, we're only going from 0 to pi in this case, so we really only need to look in the first quadrant, right? So in the first quadrant, what angle do you know has a tangent equal to square root of 3? So it's tangent sine over cosine, so the root 3 needs to be in the numerator. What angle are you looking at? Pi over 3, because the sine has to be, the sine's in the numerator, so the root 3 has to be in the numerator. So you have to have root 3 over 2 divided by a half, so it has to be the pi over 3 piece. Okay? So theta will be pi over 3. And in this case, we can just add multiples of pi, and we're done. We don't have to do the multiples of 2 pi, because the tangents period is pi. Now, say you forgot. Say you forgot, and you're like, I need to find all my solutions in 0 to 2 pi and add multiples of 2 pi. Say you forgot. Okay? Ever forget? Happened to me. Okay? All right. How would you do it in that case? Well, pi over 3 was the solution that was in quadrant 1. Where else is the tangent positive? Third quadrant. What pi over 3 angle would you have in quadrant 3? 4 pi over 3. And then add your multiples of 2 pi. And notice now I've written it backwards. Now I've done 2n pi instead of 2 pi n. Again, it doesn't matter the order. I think the book does it in the other order, but literally the order doesn't matter. This is the exact same set of solutions as this is. It's just written a little bit bigger. Okay? So again, if you forgot and did it just like what you did for sine and cosine, you'll get the same answers. It's just written a little bit differently. Okay? Notice that if you put in 1 in for n here, you get 4 pi over 3. If you put 3 in for n, you get 4 pi over 3 plus the other 2 pi, and so on down the line. You'll get half of them are of this form and half of them are in that form. You'll get the same answers. So again, if you forget that you only have to look from 0 to pi for tangent, and you do 0 to 2 pi instead, you'll still get the right answer. That's okay. All right. So let's go back up to this one. Because this one and the next one that's at the bottom of the page, we have to do a little bit of extra work. We have to do a little bit of work with our calculators. Okay? Do we know, looking at the 0.22, do we know an angle that when you take the sine of it, you get 0.22? No. We know 0, a half, root 2 over 2, root 3 over 2, 1. That's all we know, right? That's all we got. Okay? 0.22, not in our arsenal. Okay? So this is when we have to use our calculator to help. All right? So if I want to get theta in your first step here should be the exact first step that you would have done if you're trying to solve a triangle. What would I do to both sides to get theta by itself?
Inverse sine.
Inverse sine, good. And putting that in your calculator, what do you get out? Let's do 4 decimal places.
Negative 12.7090.
That's in degrees. Can you flip the radians for me? You're right. It's just in degrees. There's a reason why I want to make sure this is in radians instead of degrees. All right, so this is one solution. To find all solutions that are based off of this solution, we would add our 2 pi n again. And this is why I want it in radians, because the 2 pi is representing radians. Okay. If it were in degrees, you could do 360 degrees times n, and we give you the other ones. But this is why we want it in radians. Okay. All right, so this gives us a bunch of solutions, infinitely many. Unfortunately, this does not give us all of the solutions yet. Okay? Let's think about why and how we're going to find the other ones. Now remember, everything else that I've been doing, the first thing I asked you was, what quadrants are we looking in? Right? That was the first thing I asked you. Okay. Sine is negative, so what quadrants are you looking in? Third and fourth. What quadrant did I just find an angle in? Fourth, right? Because remember, inverse sine is 1 or 4, right? Okay. So I need to figure out what angle's over in quadrant 3. That also does the job. So let's think about this for a second. We found this angle, right? We want this angle. Either that way, or you could do the negative. It doesn't matter. This way it's probably a little bit easier to see what it's supposed to be. How would I find that angle? We're not worrying about the negative. What do I know about the size of this angle on the left and the size of this angle on the right if I don't worry about the negative? They better be the same, right? They better be the same exact size. So how can I figure out what this angle is here?
You can add pi.
Say it again?
You can add pi.
Yeah, you can add pi, exactly. And then if you wanted a decimal approximation, you could just add your 0.2218 to the pi. That's exactly how you do it. And a lot of times, personally, I think it's a little bit easier to draw the picture to figure out what you're supposed to do to figure out your angles. That's just me. That's exactly why I drew the picture.
Would it be positive 2218 because we're adding pi, or is it when we're adding pi? Would it be plus the negative 0.228, or just be the because it's positive? Okay, so notice I have to do pi plus a little bit, so I better be adding something to it. Okay. That was why I said, as in terms of angles, they have the same size. Yeah. But I don't want to call it I don't want to add a negative because that would make it go back that way. Yeah. That's a good question though. But that was why I was making sure I was talking about the size of the angle, not worrying about the negative. Other questions on that one? All right, let's flip down to the cotangent. Is 0.42 one of those that we know the exact value of? Probably not, right? So I want to, if it's not one that we know the exact value of for an angle, I want to use my calculator. If I'm going to use my calculator, that means I'm going to be doing an inverse trig function. Do you see an inverse cotangent button on your calculator? No. You see an inverse tangent button though, right? So first thing I want to do is rewrite this so that it's in tangent instead of cotangent. To rewrite this as tangent of theta, what do I need to do to the right-hand side? Put over 1.
Yeah, put it over 1. Good. Oops. It's a 0, not a theta. So make it 1 over 0.42, negative of that. And then do your inverse tangent. But what do you get when you put that in your calculator?
Negative 1.1732.
Okay. Again, make sure your calculators are in radians in this, the way we're describing the solutions, because again, we're adding multiples of 2 pi. If I'm adding multiples of 2 pi, I'm assuming everything's in radians, so you don't want this in degrees. Okay. Now, again, I said tangent's a little bit different. Tangent, you only need to figure out the solutions that are in 1 pi interval, right? We don't have to do 2 pi, we'll do 1 pi, correct? Well, inverse tangent gives you an angle in the interval from negative pi over 2 to pi over 2, which has a length of 1 pi, right? So this is all I need to do to figure out the rest of the solutions now. We just add on multiples of pi, and we're done. Tangent's a little bit easier in that regard. Again, say you forgot. It happens, right? You forget things. It's okay. Everybody forgets things. Okay. Negative 1.1732 is in which quadrant?
Third.
Fourth? Yeah, it's down here, right? All right. Where else is tangent negative? Second, right? So there will be another angle. Hey, another angle up here. And you'd be looking for that angle if you were trying to find the other one between 0 and 2 pi, right? If we try to attack it just like we did the other ones. Now, asking the same thing that I asked before. Ignore the negative. Size of this angle compared to the size of this angle. What can you say? They're the same, right? So how would you figure out what this angle is here?
Yeah, just like pi.
Say again?
Would you subtract it by pi?
I would subtract it from pi, right? Yep, exactly. So I could do, this angle would be pi minus 1.1732, right? Because it's not all the way to pi, so I would subtract it off in this case. So another way to write it, you could write theta equals 1.1732 plus multiples of pi, 2 pi, sorry. Or you could do pi minus 1.1732 plus multiples of 2 pi. That's, again, they're both correct. The first way is just a little bit more succinct, right? It's a little shorter. But again, this follows the same principle that we were just doing with sine and cosine, correct? Figure out one of them, use your knowledge to figure out the other one, and then add multiple of 2 pi to both of them. So it follows that same pattern. But if you remember your tangent period is pi, the first way is easier to write down. What questions do you have on this one? You want to do another one like this? Let's do one with cosine. I'll just make one up. How's that sound? Let's say we have cosine of theta is equal to negative 0.58. Again, like I've asked you several times today, do we know an angle that has a cosine equal to 0.58? All set right. No. So this is when we're going to use our calculator. What should we do first then?
Inverse of cosine.
Good. Inverse cosine to both sides. Good. It's actually equal to that. The approximate part, because when you put it in your calculator. When you get that in your calculator, What do you get?
.8365.
0. I think that's a little small.
2.1895.
Okay. Did you put your negative in there with it? Okay. 2. What was it again? I'm sorry.
Oh,
1895. Okay. Okay. So what quadrant is 2.1895 in? Probably easier to go back to the original. A negative sign tells you you have an angle in quadrant where? Where is cosine negative? 2 and 3, right? And inverse cosine always gives you an angle between 0 and pi, so that has to be in quadrant 2, okay? So we need to figure out the one that's in quadrant 3. All right, so let's do it this way. Draw my picture again. This angle here is 2.1895. We want that angle. Okay, so let's look at the picture again. And again, I typically draw the picture to help me. Now again, I keep equating some angles, right? And not worrying about and thinking about the size of them, not worrying about negatives or not, okay? Do you see two angles on here that should have the same size without worrying about the negative? Do you see two angles that have, actually I see two pairs of angles that have the same size. Do you have one, do you see another angle that's labeled that has the same size as a different angle? So this is the only angle I've labeled, right? Do you see another angle that's the same size as that one? If you go this way, right? Well, instead of going positive, this would be negative. So can you use that to help me figure out what the angle is? The one that's going around the quadrant 3? Yep, so instead of 360, we would use 2 pi, right? So we'd have, or theta is approximately 2 pi minus that. That would give us our other angle, and then add your multiples of 2 pi to each of those. Yeah.
Could we subtract from 3 pi over 2 instead of going around?
If you subtract it from 3 pi over 2, you can go in this way?
Yeah.
You can, but I have to figure out what that angle
is.
Yeah, yeah. And that angle is pi over 2 minus that, and so you'll end up in the same place. You'll end up with the 2 pi anyway. You could absolutely do it that way, but you're going to end up with a 2 pi out in front anyway. Yeah, that's a good question. You could do it that way. That one okay? You want to do one more like that? Or are you okay with it? It literally makes me zero difference. I know how to do it. So that's why I'm asking if you want me to do another one like that or not. Yes. No. Maybe.
You can do another cosine, I guess.
Another cosine? Sure. You want one? Sure. You want to do a positive one or a negative one?
Do a positive.
Okay. Let's say we have cosine of theta is 0.77. What do we do first?
Inverse cosine.
Okay. And get.
920.
Sounds right. What quadrant is that angle in? 1. Good. It's in quadrant 1. Where else is cosine positive? Fourth. Good. So down here. So we're looking for that angle. Or you could just dip underneath too. But let's figure out some of the problems will ask you to find all of the solutions from 0 to 2 pi, which is why I'm doing it this way. The easy way, of course, would be do the negative, right? Because this angle and this angle should have the same size. Okay. But if I'm looking specifically for angle in 0 to 2 pi, how would I get the big one, that looped around one? Yep, take your 2 pi minus the 0.6920, yep. And then again, to finish it off, add your multiples of pi. Or, sorry, try again. Add your multiples of 2 pi. So, moral of the story, when using your calculator to approximate a solution, you're going to have to go hunt for a second solution. That make sense? Your inverse trig functions only give you half the picture typically. The only exception to that is your inverse tangent if you're over a period of pi. All right. We'll do more of these on Wednesday. Otherwise, have a good one. We'll see you then.